What we're going to do today is, so if you weren't here last time, we did do a lab, some instructions there on the lab. Today we're going to do calculations on specific heat and calculations on exo and endothermic. We're going to record that. And then we're going to go into rotation, where in the red section I'm going to help you with your lab, with your assignment for today. In the green section you're going to work on a Nearpod and your quiz. Okay? So that's what we're going to do during that period. So if you'll just come back with me, grab your notes out, let's go. You will need a calculator today, so if you don't have one, grab one real fast. Oh, I need to shut that down and bring it back up. Okay, yeah, just here. Really quick, go over there and I'll put it up. Okay, go. Okay. Bring this back up again real fast. All right, so today, again, we're learning about a specific heat equation to solve for desired variables. We're going to finish our calculations on our labs if you haven't done that, because I didn't get very many turned in. The iPads are up on top of the computers that you can turn them in. And then we'll have daily work. Hopefully that by the end of the day you'll have that turned in too. Okay? So going forward, we're going to watch this little video thing here for a second. We're going to talk about it as we do so. I've got to come over here so I can get it to work. All right, so we talked about the thermite reaction. Will you guys shut that door for me, because the other class is going to be coming in to lab. Thank you. We talked about the thermite reaction going bad, remember, on the safety. This is just the thermite reaction again. It is extremely exothermic. It's iron oxide, aluminum, and a catalyst placed in a flower pot. And let's see what's going to happen here. Usually we don't do this inside because this is what happens. You'll have to wait. Grab a computer. Yeah, grab a computer. Okay, so that's a thermite reaction. Let's look at a couple other reactions. This one we used to be able to do. This is pretty awesome. This nitrogen triiodide is, you make it as a liquid and then you let it dry. And watch what happens when it dries and you touch it with something. Just a feather is coming in on a chicken stick. Okay, it's known as a contact explosive. So it is a contact explosive, and you can see the iodine being left in the purple gas is coming off of it. Okay, going forward. This is a white phosphorus in a solution of carbon disulfide. Let's see what happens with it. You can read the side here and sort of figure out what's going on.
An element dissolved in carbon disulfide is taken into a medicine dropper and used to write on a piece of filter paper. As the solvent carbon disulfide evaporates away, the element begins to react with oxygen from the air in a spontaneous exothermic combustion reaction. What is this element?
White phosphorus. That makes me laugh that they do that. So that's a really one that catches fire very easily. Another, as we go through this, I wanted to sort of give you a visual idea of what's actually happening with endo and exothermic. So when we do the combustion of methane in an exothermic reaction, we have methane, and this is a diagram shape of methane. Carbon's big and the hydrogens are attached, and it's called a tetrahedral shape. And we have two oxygens attached. We've balanced equations like this already. So what happens is energy is put into the methane with a spark or something, and that lets the hydrogens come off the methane. Then that energy is also given a little bit to the oxygen, and it's able to separate. Next, they recombine to form water, where energy is given off, and carbon dioxide where energy is given off. So as molecules form, they give off energy. As they're taken apart, they need energy. So depends on how much energy overall. So this one took a little bit of energy to get started, but it gave off a lot of energy. When you do a combustion reaction, you know you're getting off energy, right? Because it gives off heat. So let's go on to the next one. This one is one we did in lab. This is where we did that calcium carbide, or try that again, calcium chloride and the sodium bicarbonate water. This is the one we did where I told you need to make sure you put the lid on this because it's hygroscopic. It pulls water from the air. Okay, we actually made calcium carbonate and sodium chloride and water and carbon dioxide. This was the exothermic one. This was the one that was by the periodic table, if you remember that. This is the lab. We did one reaction there, and we did one reaction on the lab table right by our room. This one was exothermic. We also did another reaction where we did acetic acid and sodium bicarbonate, which was baking soda and vinegar. And we make sodium acetate, water, and carbon dioxide. This one felt cold because it took in heat from around us. Okay, so we are going to look at each of those as an endothermic process reaction and an exothermic process reaction. So endothermic takes in heat, right, more than it gives off heat. So we still need to have some energy to break the bonds. So we're going to break the bonds by putting energy in. Then we have to remake bonds, and energy is given off. So overall, our reaction for endothermic, we take a lot of energy in to break those bonds, and only a little bit's given off. So that's why it feels cold or cool to the touch. Then if we go to an exothermic reaction, we break the bonds. We still need energy to break the bonds. We make new bonds, and energy is given off. And if we look at the overall reaction, it took less energy to break the original bonds than the energy given off from making the bonds. Okay, so you got to sort of think of that. This is going to feel hot, or we're going to get light, or we're going to get sound. We're going to have some kind of energy coming off. Okay? All right, so we're going to come back to our PowerPoint here, and we're going to talk about hot hands, okay, or hand warmers. Tell me how they work. Does anybody know?
You shake them, and then like the stuff inside is inside, and it comes together, and then it gets hot.
Okay. And why does it work? Good, because right now it's sealed. The minute I open it up, it starts to come in contact with oxygen. But if I just let it sit there, the only one that comes in contact with oxygen is on the outside. So that's why they tell you to shake it and play with it, you know, to get it to work, so that more oxygen comes in contact with that. Who has cold hands? Okay. Whoops, sorry. I don't throw very well. I used to be on softball, but it's been years. Okay, I got one more that I'm going to use. Anybody else got cold hands? I'll go. Well, that table has one. You can share one out. I'll put this one over here. Okay. Yep. Okay, so now you guys that volunteered to have it, you guys get to volunteer to help keep track of the temperature. So you have a little part in your notes right there that talks about hand warmer demo. So we just talked about how that hand warmer works. How does it work? What do we need to make the hand warmer work? What do we need? Oxygen. Okay, so we needed to move it around. So would you write down what kind of reaction is it, do you think? If we need oxygen to make it happen, okay, it's probably a single displacement. Okay, we would think normally a combustion, but it's not going to catch on fire, I hope. Okay, I hope it's not going to catch on fire. But we want warmth kind of giving off. So this single displacement reaction, because we got an element oxygen that's going to combine. Okay, so those of you that got the hand warmers, you're going to need to be telling us over time what temperature is. So right now, put the temperature probe on and tell me what temperature you're at right now. The hand warmer. So wrap the hand warmer around the 27.9, and it just keeps going up. Well, we're talking here 28, 29, 20, or actually 28.6, 7, 8. So it's going pretty rapidly up in temperature. Okay? What happens with these hand warmers after time? they go down. Why? Why wouldn't it just keep going hot or stay hot? Okay, it would burn us, so there's a fail-safe in there. The people that made it said, you know, we don't want these to get too hot because then they'll have people with second-degree burns, and that would be bad. Okay, what else? Tell me what else is going on. It's not working? Okay, let me get you another one. Why? What's going on with this reaction? Is it going to keep going back and forth? What's going on with it? So try it. There we go. Isn't this a finite reaction? What does finite mean? It ends. So it's going to be a reaction that I'm not going to be able to go backwards. So this is a finite reaction. In other words, it's a forward reaction. It only goes forward. Once it's done, it's done. So it gives off a certain amount of energy. Once that energy is given off, once all the things have reacted, then it is done. So put on your caps, thinking caps. How could you, if you were to engineer this, and you had a chemical that gave off a lot of heat, but you didn't want it to give off all the heat at first, what could you do? Good, I could decrease the amount of oxygen getting in. So look at the pack right here. Tell me what the pack looks like, the hot pack.
It's like white. There's not much to it. It just says the logo.
Can you see holes all through it?
Oh, yeah.
Does it have lots of holes? Does it have little holes? Do you think a lot of oxygen could get through?
A lot of little holes.
A lot of little holes. So there is some that's not, it's more solid because whatever's in there is not falling out, right? So we could do with the packaging. What else could you do to slow down the reaction? That was a good idea. That's one of the ones they do use. They tell you to shake it up so that the inside will come back to the outside. So what could you do inside the packet to make it sort of slow down a little bit? Think about a cold pack. In order for a cold pack to work, what do they tell you to do? You have to twist it and make sure that layer pops, right? Because there's the inner layer. So couldn't you have a couple inner layers of plastic maybe that after time, if it starts getting cold, you rub it again and it pops that inner layer? Or maybe as that gets hot, maybe that melts that inner layer and it moves again. Or I can coat whatever the chemical is inside with just a little bit of wax or something to keep it from reacting right away. So then when it gets hot, the wax melts off and then it reacts. So there's a lot of ways to slow things down. Same thing with medicines in our body. When the doctor prescribes like amoxicillin, they don't want all the amoxicillin to hit your system all at once because your system will go into shock. They want it to be time released, right? So they do things to time release things, especially in capsules. They can put it so that there's a capsule inside a capsule inside a capsule kind of thing going on. Or a capsule with little beads inside that are coated with different layers of coating so they release it at different times. So this is how that works. Okay, so let's go ahead and go on forward. This is a heating curve. You are going to get this heating curve in your Nearpod. I want you to put the heating curve drawing on the back of your green paper. There's not one on your thing, but that's where you're going to put it. I'm not going to leave this up. You're going to do that on your own, in your own space and time, on the back of the green paper. Okay, so just know that's where I put my heating curve because you're going to be held responsible for it. Okay, but that's all the Nearpod. So we're going to talk about specific heat. This is a bunch of definitions that you need to get down. We didn't get this down before we went into lab because we had to go in before the other class. But basically, specific heat is how much energy does it take to raise 1 gram of a substance 1 degree Celsius. Or we could put 1 degree Kelvin because they're the same as far as intervals. Metals usually have a low specific heat. We worked with metals last time. Metals have usually under 1 as a specific heat. Water has a high specific heat. Anybody remember what water's specific heat was from the lab? Well, that's where it boils. 4.184, that was water-specific heat. So water is considered high as far as a specific heat, how much energy is needed to raise 1 gram 1 degree Celsius. Okay, I'm going to go to the next page where it actually has an equation. This equation was also on the front of your lab, but you need to write down what it means. Now, this right here, this Q, could also be labeled delta H. So you'll hear me use both of those interchangeably because they mean the same thing. Q is the amount of energy in heat, or heat energy. Delta H, change in energy of heat. M is your mass. C is your specific heat in calories per gram degree Celsius, or joules per gram degree Celsius, or joules per gram degree Kelvin, or calories per gram degree Kelvin. Okay, so we can have a lot of little changes there. Calorie is more an English system. Joules are the SI, or System International. Kelvin we usually use for absolute temperature, so we don't have to worry about zeros. And that helps with delta T, because if we have a 0 in there, that's not good. Delta T is always the temperature final minus the temperature initial. You'll need that today because we're going to do some problems with that. Again, if you don't have a calculator, today we're going to start using calculators, so jump up and grab you one if you don't have one. They're right behind the computer cart. And at the bottom here, if delta T is negative, that means heat is lost. Q is negative. If delta T is positive, that means heat was gained, and Q is positive. Okay, we're going to go into the Q is negative and Q is positive more on the next page, so if you don't get this down at the bottom, you're okay. Has everybody got the equation and the delta T down? Because that's important. Okay, I'm going to move ahead. Is that all right? Has everybody got that down? All right, so this is the endo and exothermic. So exothermic energy is released, surroundings are warmed up, Q is negative because the system is losing heat. Q is negative because the system is losing heat. So that was down at the bottom. And endothermic is energy absorbed, surroundings are cooled down. Q is positive because the system is gaining heat. Okay? Excuse me. It's a good thing it's Friday, right? All right, so we need to be able to do some problems. We started with a hard one, which was the lab, where we took two equal to each other. We're going to start with some simpler ones. We okay to move forward? Okay. All right, here is the first one. They are story problems. You know I hate story problems, but learn to decode story problems by taking out what you have. So as I'm reading, 38.8 gram. Oh, that's my mass. 38.8 grams. Piece of metal alloy absorbs 181 joules. Oh, that's Q. Q is the amount of heat, so I can either say delta H or Q, it doesn't matter which one you use, is 181 joules. As the temperature increases from T1 or Ti to Tf, okay, so Ti is 25 degrees Celsius, Tf is 36 degrees Celsius. Before I go on, I know, oh, delta T is Tf minus Ti, so 36.0 degrees Celsius minus 25 degrees Celsius, that's 11.0 degrees Celsius. And then it says, what is the specific heat? So I am looking for CP, question mark. So all I've done is pulled everything out of the story problem that I need. So then I go back and say, okay, well, what's my equation? Well, my equation was Q equals mCp delta T. But I need Cp, right? So in math, they taught me that if I need something and it's times by other things, then I can divide both sides by what it's times by. So I'm going to divide this side by m delta T, and I'm going to divide this side by m delta T. By doing that, mass cancels with mass, delta T cancels with delta T, and I can rewrite the equation saying Cp is going to equal Q divided by m delta T. Everybody okay? I'll back away and let you write for a minute. At this point, all I have to do is put in what I've got. So I'm going to put in Q, I'm going to put in M, and I'm going to put in Q, I'm going to put in M, and I'm going to put in my delta T into the equation that I just solved for. So plugging in here, 181 joules divided by 38.8 grams times by 11.0 degrees Celsius. But I need to remember when I hit that divide sign, that whole thing on the bottom needs to be in parentheses. And we'll end up with Cp. None of the units cancel, so I'm going to have joules divided by grams degrees Celsius as the unit. How many significant figures do I need to report? 3. Good. So what is my answer here? Is it bigger than 1 or less than 1? Most often Cp is less than 1. So if you get something bigger than 1, you know you've got some problems. So what did we end up with here? 424? Do I have a second on that? Awesome. Okay, so there's our answer for the first one. All right, we okay to go forward? We need a few minutes, it looks like. Get the last of it down. I still see head bobs. Okay, everybody okay to move forward? Okay, the next one, same thing. We're going to pull stuff out. So graphite has a specific heat. What was specific heat? Cp. So Cp equals, so here's the specific heat right here. I'm going to rewrite it over here, 0.709 joules per gram degrees Celsius. And I always rewrite it out. If you want to circle and put the letter by it, that's fine. I don't want to look back up at the story problem after I've read it. Okay? So if, here's a number, 25, it wrapped, grams. 25 grams is what? M, good. It's my mass. So 25 grams of graphite cooled. Okay, it's cooled from T1 to, or Ti to Tf. All right, I'm going to put those over here. Ti was 35 degrees Celsius. Tf was 18 degrees Celsius. Okay, delta T is Tf minus Ti. That means 18 degrees Celsius minus 35 degrees Celsius. So I'm going to end up with a negative 7? 17. I was going 7's a little small, but that's okay. All right, 17. Then it says how much energy. What was energy? What was the symbol for energy in our equation? Wasn't that Q or delta H? I don't care which one you use. So I'm trying to find that. Well, that equation was already set up that way, wasn't it? It was Q equals M Cp delta T. So I'm just going to plug in M, Cp, and delta T. So I plug it into my equation. Q equals 25 grams times 0.79709 joules per gram degrees Celsius times by 17 degrees Celsius. Double checking that my units cancel here. And I'm left with joules. That makes sense. So Q is going to equal joules. How many should I report to? Yes? Thank you. It should be negative 17. I just looked here. You are right. It should be a negative 17. So we should end up with a negative number. Does that make sense? If it's cooling, it has to give off energy, right? What do we get? Negative what? 301. Do I have a second on that? 301. Yes. Awesome. Okay, so that's my answer here. Now, there's one problem that's really hard for a lot of students, so I'm going to do it with you. It's the last problem in your practice, so if you'll turn to number 5 in your practice, I'm going to teach you how to do these kind. Okay, they're not hard, but they're a little bit different. Okay, so again, we're going to go through. What's this first number? Mass. Good. So mass is equal to 335 grams of water at, oh, what's that? TI. Okay, 65 degrees Celsius. Loses, what is this number? What was joules? What do we measure in joules? Q. Good. So Q is 9750 joules. What is the final temperature? Ooh, TF is what I'm missing. Of the water. Liquid water has a specific heat of, and specific heat symbol was what? CP. 4.184 joules per gram degrees Celsius. So remember our equation was Q equals mass times specific heat times change in temperature. And remember that change in temperature equal TF minus TI. So, yes. Okay, let's do that then. Yep, that's good. So yours said 65.5 degrees Celsius. Okay, we'll put that in. I'll just pretend that mine has 0.5 up here too. Okay? All right, so here's the thing that I do. You could be a math scholar and put that delta T, change that out for TF minus TI, but then you'd have to do distribution and blah, 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 blah. I don't want to do all that. So I just solve for delta T because I got to find delta T. Okay, so I'm going to rearrange this equation so that I'm solving for delta T. To do that, I'm going to divide both sides by the MCP. By doing that, mass cancels, CP cancels, and I've got delta T by itself. So I can say delta T is equal to Q divided by MCP. And I can come over here and I've got Q, and I've got M, and I've got CP that I can plug in. So I plug them in. 9750 joules divided by mass was 335 grams. That's a G, by the way. That got erased. Times by 4.184 joules divided by gram degrees Celsius. Remember again, when you hit the divide sign here, this needs to be in parentheses. Looking at my units, grams cancels, joules cancels. It's 1 over 1 over degrees C, so I should end up with a degree C here that equals delta T. That's not my final answer, though. And if it loses energy, we should be doing something else here. If it loses energy, it means it's giving it off. So this should be a negative. Right? Because it says up at the top it loses that much energy, so it's giving it off. It's exothermic. So Q needs to be, or delta H needs to be negative. So we're going to end up with a negative delta T. So negative something. Has anybody got a number? 6.96. Do I have a second? Anybody? Yes? Okay. All right, so we're not done. Now we've got to come down to this equation right here. And I'm trying to solve for TF. Okay? So when I'm trying to solve for TF, we're going to add TI to both sides, right? And when I do that, TI over here cancels out. And we end up with TF equals delta T plus TI. Are we okay with that? So now all I have to do is go, oh, delta T, So that was minus 6.96 degrees Celsius, plus my original temperature was 65.5 degrees Celsius. So what do I end up with?
58.5.
Okay, and since we only had 3, so 58.51, so 58.5 degrees Celsius. Okay, well, does that make sense? If water loses heat, should it get colder? Yeah, it should get colder. So we did a good job. All right, so we're going to split now, and we've got 45 minutes, so about 22 minutes in each. So I'll set the timer for 20. That'll give us some moving time. Red, you are working on your assignment right here that you're doing right now, and your lab. Green, you're working on the Nearpod, which you can access by going to your, let me go forward here. By the way, your turn. Finish up your daily work, blah, 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 turn it in.